nice words, Sergey, and thank you for organizing this meeting. This has been very enjoyable. And so I will change a topic a little bit. I'm not going to talk about too much any applications, no drugs. Certainly these polymers I'm talking about, they are not edible or not healthy, I'm afraid. This is mainly physicochemistry of polycations in water. And as we know already, we have had nice lectures about, especially Francois' lecture yesterday about thermoresponsive polymers. We have in principle two types of such in which are responsive in water. They are polymers which show either a lower critical solution temperature or upper critical solution temperature. Typical for these LCST polymers is some sort of hydrophilic hydrophobic balance, which can be changed with temperature. And on the other hand, for these UCST polymers, there are some sort of interactions between the polymer chains that prevent the dissolution at low temperatures, but which interactions can be broken with temperature. And so I will talk about polycations. And these are polymers which are often called polymeric ionic liquids.
Heikki, sorry to interrupt you. Can you start your presentation, because we see just slides. Maybe you should go to slideshow and make it running.
You see only slides?
Yes, we do.
There was something wrong with this share screen.
No, I think it was okay, but it was just you should go to the slideshow and make it running. Oh yeah, that's better.
Is it not good?
Yes and no, because we see the so-called presenter's view. So maybe.
Sorry, I see as it's.
So you right.
Once again.
No problem, no worries.
Well, I noticed that there is something strange in this.
So I would suggest start your presentation now, and then using Zoom.
How about this?
Yeah, that's perfect. Awesome. Yeah. Right.
Okay, now it works.
Yeah, it works. Perfect.
I got mixed because I have two screens. On the other screen, I see now myself, and then the other one, the slide. But okay, so what I was saying is that the polymers I will talk about, they are often called polymeric ionic liquids, but we prefer talking about just simply about polycations. And I start by showing one polymer we made already some years ago, maybe the first polyionic liquid we studied. We made a diblock copolymer of this imidazolime containing polymer and polynipalm, and we studied the thermal behavior of this as a function of the length of the polynipalm block. I don't go into details, but these polymers, when they have a hydrophobic counterion, here it's tetrafluoride, it is insoluble. If you change it into bromide, for example, it's water soluble, but this turns it insoluble, and as we see, the polymer forms nice raspberry-like micelles in water. Heating this system causes dangers, of course, because we have the polynipalm which collapses, but here this should be taken very critically. Here's zeta potential data on two of the polymers as function of temperature. this is now simplified because using zetasizer with this kind of polymers that change their size with temperature, it should be done very carefully. But whatever, we can see that when we heat the system, the cationic charge on the particle surfaces decreases. So it not only tells that when polynapalm collapses, the polycation turns to the surface of the particle, but it also tells what we then realized is that the solubility of this ionic liquid block increases with temperature. And this kind of led us to the studies of the UCSD behavior of these polymers. I said we have not studied applications, but because anyways, always somebody asks, what can you do with these polymers? I took one recent example review of polyionic liquid composites. Everybody knows that ionic liquids are good solvents. In my university, people study, they synthesize new ionic liquids and study, for example, dissolution of cellulose into these, a process which has led into fabrication of cellulose textile fibers with ionic liquids. So also polymeric ionic liquids can act as solvents, and it is a way to this kind of composites. It's a very good recent review of those. So polycations are polyelectrolytes, and polyelectrolytes, they are of course extremely soluble in water. However, this matter has been studied already quite a while, and it was already in the beginning of this century when it was reported that these polymers may be turned insoluble with certain counterions. This was studied quite a lot with for example, this kind of polymers with imidazolime side groups and boron tetrafluoride anion. There are several reports where it was seen that the anion makes the polymer thermoresponsive, and the response is very much dependent on added salt. And this is actually important. When the salt concentration is low, it usually decreases. UCSD, which is as mentioned here, because the counterions, chloride and that hydrophobic one, they compete with each other. Then when the salt concentration is high, this turns upside down. There have also been some early studies on polycations with LCST. And also in this series, maybe it was interesting to study two very different strong polycations shown here, where we observed that we can either turn them totally insoluble or we can make them thermoresponsive by the choice of the counterion. And I want to show one very recent work. It is it will come out in polymer chemistry now in these days. So you can find it already as advanced article. This is a work where a series of polycations was synthesized. You see here alkyl substituents of this nitrogen, and the length of this alkyl chain was varied from ethyl to pentyl. And interestingly, this is really nice finding that when the substituent is ethyl, this polymer shows UCST. Then with increasing length of the alkyl chain, this changes into LCST, the hydrophobicity of the polymer increases. So in this case of a short alkyl chain, the electrostatic interactions, they govern the system. However, then with more hydrophobicity, it is now then this hydrophilic hydrophobic balance that gets important. So ethyl substituent is here, and this is, for example, pentyl substituent. It gets hydrophobically hydrated and shows LCST behavior. So, phase separation of polycations, it can be induced with counterions, and here are the important counterions. These are ones which are very much used in ionic liquids in general, and I will mainly be talking about this one, this triflate, which we have used quite a lot. And here once again we see how a water-soluble polycation with, for example, chloride or bromide ions, when we change the counterion, it turns less and less soluble and can show UCSD behavior. Of course, people have synthesized a lot of this sort of polymers, like polymers with UCSD and both UCSD and LCSD behavior, polymers which were formerly called schizophrenic, but no more. We have learned to call them nowadays oppositely responsive polymers. But the polymer I will pay attention on now is this one. It is like from the previous series of polymers, the one which I did not show yet. By the way, in this table I showed, I forgot to point out this, that here, this one. If you look carefully, you can see that we've also studied the effect of various counterions. So some people are very interested on this Hofmeister series, and if you look this carefully, you can see, do the polymers follow the Hofmeister series or not? There is however, so much unknown things in this Hofmeister that I don't want to go into that. But I will talk about now this one, which only has methyl substituents, and as you see, it is a diblock copolymer, polyethylene oxide and polycation. And note there is also a hydrophobic end group, which comes from the chain transfer agent. And the question that interested us was that if we can turn this polycation hydrophobic, does the polymer behave as they normally do, that they self-assemble into spheres? That would it, for example, make it possible to run PISA polymerizations, of which we heard a great lecture yesterday, if this happened. The polymers, they behave strangely in water. And actually, this slide almost tells the story. After this one, I will just add some details. We have made a series of these polymers with varying the length of the cationic block, and this is the first one we made. And you can see from the photo at high temperature, 55 centigrades, this is extreme. It is totally soluble. We get a clear solution. We start to cool down the system. The solution turns turbid, and at some instant less turbid, which is kind of disturbing. So there are two processes going on. This is the synthesis, if you can see these details. So we use two different chain transfer agents, the shorter one and this one with polyethylene glycol. And so we get the in the latter case, we get this double copolymer with also the alkyl chain. And why this is not a pisa polymerization, it should become clear during the rest of this presentation. Now I have difficulties to move further. Sorry, my computer is thinking. Okay. Whew, here it is. So I give you this table. Don't worry, tables are no good in presentations, but I want to show this just because there's only one number to check, and it is this degree of polymerization of the polycation, which is here. So we have 4 diblock copolymers. The first one is this A, where the degree of polymerization of the polycation is 81. This is the one with which we started, or which we saw the photographs. And after seeing those solutions, we wanted to make more polymers. There are 2 with longer cationic block and 1 with shorter cationic block. Well, the transmittance curves, when we cool the system, they are, one example is here. Here is the transmittance of a polymer solution during cooling with different triflate concentrations, added lithium triflate concentrations. High salt concentration, just UCST, and then at lower salt concentrations, we see this weird behavior. The system turns turbid and then clarifies again. I'm sorry. This is now a slow computer. I apologize. This is really slow now. But actually, this is what took so much time to get loaded. Here are the same, almost the same transmittance curves, but now this is as function of polymer concentration. We have fixed the salt concentration to one where we saw this strange behavior, and we check it with polymer concentration. We can see even steps in this process, and here are the DSC traces of the heating and cooling, and also here we can see some sort of 2-step process. We also had a look on this by light scattering. Here, in an experiment where we put the solution into hot goniometer in light scattering instrument at 55, and then we started to cool the system. We see the scatter light intensity suddenly increases. There is a spike. It increases, decreases, and then levels somehow. And the same is true when we heat the system. Here are the size distributions by measured by a Malvern instrument. 55 centigrades is here up, and here, of course, this one, the lower peak here, it shows the real size of the molecule. This is comes from the polyelectrolyte nature of the system. So we see at room temperature, particles are of this size, then they increase very much upon cooling, and then decrease again. So what is going on in this system, and what is going on in my computer, because it's really slow in changing slides, I'm sorry. This one, actually, this one shows the behavior of the just homopolymer, the homopolycation, the transmittance upon cooling. We see only this one-step process, or very clearly seen in the DSC curves. And if I manage to move on, this has something to do with the difficulty I had in starting this show. This slide shows that the importance of having a block copolymer. The transmittance of our block copolymer solution is shown here. It's a little bit faint, but it is similar curve as we have seen before. And we can compare this. There are several samples, but this is interesting here, the black one, because this is a mixture of this PEG CTA plus the homopolymer. So we see just the homopolymer UCSD, which tell us that the block structure is essential for this, to observe this strange phenomenon. Now, if my computer allows, I will go further. Do you still see this?
Yes, we do.
Restart the probe.
Okay, it's coming.
Sorry, I've used my time now. So this just is something that has been said already. At high temperature, the polymer is dissolved, then it forms big particles, and then it forms small particles. When we shorten the polycation block, we see practically similar behavior. These transmittance curves, they're really quite terrible, but we see the same fact. We have clear turbid, less turbid solutions when changing temperature. The bigger polycations, they behave as this polycation, homopolycation. They only show the UCSD behavior. Here are the both. So, so the length of the polycation is important. And here it's collected all these 4 polymers we have used, the long ones and the short ones. I would love to show you more, but
Heikki, how many slides do you have more?
not many, just a few.
Okay, cool. So
I will finish in time.
okay, great. Thank you.
Of course. Yeah. Of course, my computer doesn't agree with me, but
Oh yeah.
Okay, now I skipped already a few slides, so I will be in time. So once again, let's have a look on the size distributions of these polymers as a function of temperature. Here are the here is the shortest polycation on the left-hand side, and here are the 2 longest polycations on the right-hand side. The left-hand side polymer behaves as we saw already with dissolution at high temperature, and then these strange changes. These are these are different with these long polymers, but now I'm getting worried that I tried. Yes, I apologize. Now this story is not as it should, as I was expecting, but here are important NMR spectra which tell a lot what is happening. This figure A, it is the shortest of the polymers, and these B and C, they are the two longest of the polymers. And in all of these, you can see that the PEG signal, which is this one, and note these are always in aqueous triflate solution. This PEG signal, it splits into two. And coming from here, from the short polymer to longer and to longer, we see that when we increase the length of the polycation block, this peak increases intensity, showing that this comes from the PEG that is interacting with the cation. In just pure D2O, this kind of splitting is not observed. And now, even though this presentation was not a full one because of this, what is happening again, I'm trying to change the slide. I try to come to a conclusion concerning this. And actually my time is over just now. But if you, dear Chairman, allow me to wait that I get this last slide.
Okay, you should ask this question to Robert Luxenhofer, who will be talking after you. Yes, you have a couple of more minutes, I think. I will be generous.
I cannot promise on the behalf of this computer, but even 1 minute should be enough.
It's okay. Take your time.
Close the program. Restart.
Well, Robert just promised to give you all the time he has. So
no, I will tell you what I see on the next slide, but you don't. So this considering this NMR spectra, we can see, of course, that indeed polyethylene glycol and this polycation, they strongly interact with each other. The spectra show that this interaction is mediated by the counter ion, the triflate. Without triflate, we don't see anything. And I asked in the beginning, can we make polymers that if the cation block is insoluble, they assemble into spheres with PEG shells? Well, yes and no. We can do that if the polycation block is short enough. When it's short, we get particles that are covered with polyethylene glycol, and they are stable particles. However, then when the polycation block is long, we get these two polymers, they mix with each other. We get bigger particles with where the PEG is hidden inside, and they are stabilized with charges, cationic charges, and so they are in the presence of salt, they are not as soluble, they are not as stable as those shielded with PEG. So, and this also finally answers the question why PISA polymerization is not possible. It's not possible in a case where macro chain transfer agent interacts this strongly with the growing other block. So for PISA polymerizations, we need other macro chain transfer agents. So I apologize all this inconvenience and cost, and thank you. I want to thank Erno Karjalainen and Vikram Badam who have made most of this work presented here, and I try to close my computer so that you can continue your conference.